Hello everyone, welcome back to the lecture series on magnetism in condensed matter physics. In the previous video, we have started our discussion with magnetism in metals. Now in this particular video, we will talk about Pauli's paramagnetism. This is the effect seen in most of the metals. In metals, there is an additional contribution to the magnetic susceptibility from the free electrons in the conduction band. These free electrons in the conduction band give rise to two effects. The first one is Pauli's paramagnetism, and the second one is the Landau diamagnetism. The Pauli's paramagnetism is the effect associated with the spin of the conduction electron, while Landau diamagnetism is associated with the orbital motion of the conduction electron. Here you must remember these electrons are not localized but delocalized, and these non-localized electrons do not react independently to the external magnetic field. It is because of the Pauli's exclusion principle. So, keeping this in mind, we will derive the expression for the magnetic susceptibility for Pauli's paramagnetism. Now, the origin of polyparamagnetism in metals arises because electrons feel energy state up to the Fermi energy, and without a magnetic field, spin up and spin down electrons are equally populated. So, therefore, in the absence of magnetic field, there is no net magnetization. Now, applying a magnetic field causes the Zeeman splitting of these spin up and spin down states, thus resulting in shift in the energy, and this imbalance produces a net magnetization. Therefore, it is known as Pauli's paramagnetism. Here, note that the splitting is exaggerated just for clarity, but in reality, the splitting is very small. Now, let's derive the magnetic susceptibility. Initially, we will neglect the orbital contribution and will take G is equal to 2. Now, for smaller fields, the additional energy for the electrons from the interaction of electron spin and the magnetic field is given by delta E is equal to minus of B dot, the magnetic moment of electron. And since the magnetic moment of electron is given by minus GE mu B divided by h cut times s vector, and since s can take values plus minus h cut by 2, so therefore the splitting energy will be equal to plus minus mu BB. So therefore, when the magnetic field is applied, the energy of electrons is raised or lowered depending upon its spin. So this gives rise to the paramagnetic susceptibility of electron gas, and it is known as the Pauli paramagnetism. Now the number of extra electrons per unit volume with spin up will be given by n up equal to half of density of state at the Fermi level multiplied with mu BB, and this must be equal to the number of electrons per unit volume deficit with spin down, which will be given by half of density of state at Fermi level multiplied it with mu VB and with a negative sign. So this imbalance will create the net magnetization as mu B times n up minus n down. And using equation 1 and 2, we will get density of state at Fermi level multiplied it with mu B square times B. So this will be the magnetization, which is present only if the magnetic field is present. So therefore, the Pauli susceptibility will be given by chi p equal to m divided by h, and which will be equal to mu naught m divided by b. So this will be equal to mu naught mu b square times the density of states at the Fermi level. And if you remember, we have calculated the density of state at Fermi level in our previous video as 3 by 2 n divided by EF. So therefore, the Pauli susceptibility will be given by mu naught mu b square times 3 by 2 n divided by EF. Now if we substitute the values of mu naught, mu b, the density of typical conduction electrons in metals, and its Fermi energy, then you will get the Pauli susceptibility of the order of 10 raised to the power minus 6. So which is very small than 1. Also if you see the equation 4 for susceptibility, you will see that it is temperature independent. Pauli paramagnetism is a weak effect, much smaller than the paramagnetism observed in the insulators, which follows Curie's law. This is because in paramagnetic insulators, at least one electron on each magnetic atom in the material contributes to the susceptibility. But in metals, it is only the electrons close to the Fermi surface which plays a role in determining the susceptibility. The small size of susceptibility for most metals was puzzling until Pauli pointed out that it was a consequence of the fact that electrons obeyed Fermi-Dirac statistics rather than the classical statistics. Now let's see the effect of Fermi-Dirac statistics and the crossover between Pauli paramagnetism and the localized moment behavior. For that, let's rederive the number of electrons per unit volume of each spin state. The number of electrons per unit volume of each spin state is given by integrating the density of states multiplied with the Fermi distribution function. Here the factor of half comes because there are two spin states, and for up spins the energy is E plus mu Vb, while for down spins the energy is E minus mu Vb. Now as we have told earlier also, this imbalance between the spin up and spin down electrons creates the magnetization, which is given by mu b and up minus and down. Now we can substitute equation 1 in equation 2 so that we will get mu b divided by 2 integration from 0 to infinite g at e minus mu b minus g at e minus mu b and multiplied with the distribution function. Now if you see here, we can replace this with the derivative, because if you remember from the first principle of derivatives, limit delta x tending to 0, f of x plus delta x minus f of x divided by delta x is approximated as the first derivative of function f with respect to x. So therefore here also we can do the similar situation by assuming that the magnetic field value is very small, so that g of E minus mu Vb plus 2 times mu Vb minus g of E minus mu Vb divided by 2 times mu Vb in the limits when 2 times mu Vb is tending to 0, we can approximate it to be the first derivative with respect to the energy. So therefore the magnetization will become mu b square b times the integration from 0 to infinite first derivative of density of state with respect to energy times the distribution function. Now we can solve this integration by using integration by parts. Here we will assume that this is the second part and this is the first part. So integration by parts will give now if you remember, the density of state for energy equal to 0 is 0, and the distribution function for large energies is also 0. You can verify this from the graphs also. So therefore this first term will be equal to 0. So therefore we get the magnetization as mu b square b, then the integration from 0 to infinite of minus first derivative of distribution function times the density of states. So in order to calculate the magnetization, we need to find the first order derivative of the Fermi distribution function with respect to energy. And if you see here in the graph of Fermi distribution function, then the first derivative of it will be a Dirac delta centered it at the chemical potential. So therefore this shows that the magnetization depends on how sharply the Fermi function changes near the Fermi energy. Now we can solve this equation number 4, known as degenerate and non-degenerate limits. So let's see the first case, which is the degenerate limit, which corresponds to low temperatures or the temperature approaching to the absolute zero. So in that situation, we have already seen that the negative derivative of Fermi distribution function is a Dirac delta function centered at the Fermi energy. So therefore equation 4 will give magnetization as, which will be equal to mu b square b times density of state at the Fermi level. This is the same equation which we got in the previous section when we discussed it about the Pauli's paramagnetism. You can see it here in the equation 3. This is the same equation which we got when we considered it the degenerate limit. So therefore this corresponds to Pauli's paramagnetism, where only the electrons near the Fermi surface contributes to the susceptibility. The susceptibility in this case is temperature independent and is proportional to the density of states at the Fermi level. So therefore you can conclude that the degenerate limit is corresponding to the Pauli's paramagnetism. Now let's see what happens in the non-degenerate limit. We have seen in the previous lecture that in this non-degenerate limit, the Fermi function reduces to the Maxwell-Boltzmann function. So therefore, the Fermi distribution function can be approximated as e raised to power minus of E minus mu divided by kBt. And if we take the derivative of this, we will get the same function times minus of 1 by kBt. So therefore, the negative derivative of Fermi distribution function in this non-degenerate limit will be equal to f divided by kBt. So therefore, we can substitute equation 7 in equation 4 to get the magnetization in the non-degenerate limit as, so the simplification will give magnetization equal to mu b square b divided by kBt, and then the integration of multiplication of Fermi distribution function and the density of states. And if you remember, this is nothing but the number of electrons per unit volume. So therefore we will get the magnetization in the non-degenerate limit as mu b square and b divided by kBt. So therefore the susceptibility in this case will be given by n mu naught mu b square divided by kBt. So therefore if you see here, the susceptibility is inversely proportional to the temperature, which is nothing but the Curie's law. Also, the susceptibility in this case is equivalent to n localized magnetic moments, each of magnetic moment mu b. So this implies that in the non-degenerate limit, the electrons behaves like a localized magnetic moment, while in the case of degenerate limit, the magnetic moments behaves as delocalized. As we have told you earlier also that the degenerate limit is followed by most of the metals at all temperatures below their melting points, while the non-degenerate limit is mostly followed by the insulators and the semiconductors. So therefore, you can see the crossover that in the degenerate limits, metal shows Pauli's paramagnetism, which is a weak and temperature independent susceptibility phenomena. While in the non-degenerate limit, electrons behaves like localized spins, showing Curie's law. These degenerate and non-degenerate limits are characterized by the temperature and the electron density. So therefore, this crossover explains why certain materials shift from metallic-like magnetism to localized moment behavior, depending upon the temperature and the electron density. Now, this Pauli's paramagnetism theory will form the basics for advanced theories like Stoner's criteria for ferromagnetism, where we will see how bands in some materials can become spontaneously spin splits that we will discuss in the next video. Thank you so much for watching this video.